All right, everyone. It is 2 o'clock. It is Wednesday, the 21st of April. And what we're going to be doing today is covered in chapter 10 in your book. And what we are dealing with is hypothesis testing between two samples. Okay. And this happens quite frequently. Just hold on a second here. Something popped up on my screen. Okay. This happens quite frequently in business. And oftentimes we are trying to test two different things. Okay. Maybe we are testing the quality of paint that we are putting on roadways, right? And we will have two different brands, and we want to test to see whether one brand lives longer than the other, has better wearing things or whatever. And we want to see if there is a difference between items. I talk about left Twix and right Twix a lot. Okay. I've been getting junk mail calls all day long here. Let's turn that off. Sorry about that. I lost my train of thought. That's why I should actually, turn this completely off. Sorry about that. Okay. Let's start over again because I lost my train of thought. All right. I was saying this happens quite frequently. We have two things we want to compare, right? And we want to see if product A is better than product B, right? And we don't necessarily know the great details of each one, but we want to say, well, is there a difference? Doesn't matter. Is there a difference between buying Rice Krispies and the generic crispy rice, right? Is there any difference between those? Right. We want to maybe see, are we paying our women the same as we're paying our men? Right? Okay. If you're in HR, those are types of issues you want to see, whether there's any kind of implicit bias in those. Right? So in business, we are seeing this a lot of times. Right? And so what we are going to be doing is doing hypothesis testing. Now, in hypothesis testing, when we are in this type of a situation, we are up here at the null hypothesis. If the null hypothesis is it doesn't matter, the two are equal. The two have the same mean. Okay? The null hypothesis would be that these two are equal. Remember, these are the real differences. mu1 is the real average from population 1. mu2 would be the real average of population 2. Right? And we want to know, are they the same? Or maybe is one better than the other? Or we may want to know, is one better by a certain amount, right? We may have these different hypotheses that are either null hypothesis or their alternative hypothesis we want to prove, right? Again, the alternative hypothesis is what the burden of proof is, that if you wanted to prove something beyond a doubt to a skeptical person, you would have to be taking the role of the HA, the alternative hypothesis. H0 is what we will continue to believe unless there is strong evidence to tell us we shouldn't believe that, right? So these two, H0, HA, are the same as we would have before. The null hypothesis is what we would continue to believe if there was not strong evidence against it. HA, we will believe only if there is strong evidence that H0 is not likely to be true. Right? Okay. Well, when we are comparing two means, we have equal signs, right? Mu1 equals mu2, it might be the null hypothesis that they're both the same. The alternative would be that mu1 does not equal mu2. For this section of the class, we use a little bit of a trick. And the trick that we use can be seen right over here, right? We look at if mu1 equals mu2, then the following is true, that mu1 minus mu2 has to equal 0, right? mu1 minus mu2 has to equal 0. If mu1 does not equal mu2, if these things are different, then when I subtract off mu2 from both sides, I have mu1 minus mu2 is not equal to 0. Right? So when we look at this and we look at the parentheses behind them, we can look down here that this variable, which is mu1 minus mu2, and when we look at the samples, x1 minus x2, this is the real difference, according to the null hypothesis, which we may accept or may not at the end. When we look at our samples, we can get a sample from each group. Again, just like when we were doing confidence intervals of figuring out how much different two samples were, we're going to have to take a sample from each group, right? 1 and 2, which is why we start having these subscripts. Tells us which group we have taken the sample of and what the null hypothesis said the mu was, right? So when we do this, we will end up making a hypothesis test. All of the first steps that we went through are all going to be the same. We're going to need to decide, first of all, is this a hypothesis test question? Are we testing a hypothesis? The answer is yes or no. It might be a confidence interval question, right? Got to make sure you're answering the right questions. Second thing, is it a one-tailed or a two-tailed test? Do we have an equal sign over here, or don't we have an equal sign? And if the answer is we don't have an equal sign, okay, then it's going to be a one-tailed. If it's a less than or greater than, we're going to have a one-tailed. When it is a equal sign, then we're going to have a two-tailed, right? One-tailed or two-tailed, same as before. Right? In this case, we're probably also going to want to know, are we going to be dealing with S or sigma? And just to make this part of the class a little bit easier, I am going to only show examples where either we have sigmas known or where our S's are going to come from a large population. I'll talk a little bit about pooling in cases of small populations and so forth a little bit later. But we're going to simplify things a little bit, okay? In terms of the types of problems that we'll show. All right. So we figure out this, okay? I just basically said we're going to use Z tables because I'm going to say, N is going to be either large, which means we could use S instead of sigmas, or we know the sigmas, right? So, in our world, the types of problems I'm going to give you here are going to assume that we're always going to go to the T table, the Z table instead of the T table. And again, by going to the Z table, the way to cheat is to go to the T table and look down on the bottom row. Okay. All right. So we have this, right? We draw, we're going to have the distribution of x1 minus x2 bars, right? And we draw the rejection regions. If it's two-tailed, we have both scenarios. If it's one-tailed, right, we have to decide which direction it goes in, right? And again, the best way to figure out which direction is shaded is by taking the extreme examples, right? So, so that's how we would do it, right? Anyways, once we have this, we have to find the Z cutoff values. Okay, one is going to be, this is going to be the negative of that one down there, right? And then this is going to be the acceptance region and rejection region, right? So everything is going to be pretty much the same until we get to this point. We will then go and calculate what the test statistic looks like, right? And the test statistic in your book is found, it's 10.2-ish on page 359. I am going to improve that formula just a little bit, and I'm going to write that on the board right now, okay? And then I'll tell you that what I wrote on the board is essentially the same thing that the book has, except you can use it more often than the one that the book has. The book is looking purely for cases where you're looking to see if these are equal, or you don't necessarily have a possibility of looking for something that is something other than 0 in terms of the difference. But I'll show that to you in 1 second. The test statistic now. Z-test, right? At this point, you went out to sample 1 and you got an average, right? You went out to sample 2, and let's say we got a sigma 1 and a sigma 2 from the 2 samples, right? This one here was our best estimate for what? This was our best estimate for mu1. This was our best estimate for mu2, right? So, what does our Z formula look like? The Z-test formula, test statistic, equals, okay, x bar 1 minus x bar 2 minus sigma 1 squared So this formula here, okay, is more complicated than the formulas that you had before because we are now dealing with two populations, right? This first part is what you got from the samples. This is the difference that your sample said you had. This over here is the difference the null hypothesis said the populations had, right? Mu1 minus mu2 is the difference. Mu1 is what the null hypothesis thought about one versus the other. This difference comes from the null hypothesis. What was the original null hypothesis? Mu1 minus mu2 equals 0, right? Well, if that is the null hypothesis, then that is 0. If the null hypothesis here is that mu1 equals mu2, you're going to be subtracting off a 0, which is the way that the formula in your book says, right? The formula in your book is parentheses x1 minus x2 or parentheses minus 0. Why? Because your book is assuming in this part of the chapter that you are testing to see whether they are the same or not the same, right? But if you were testing that mu1 minus mu2 equaled 1, which would be the reasonable thing if you were that third grade teacher where we were measuring students after a year's worth of instructions versus students coming in and seeing if that delta between graduating students and incoming students was over 1 year. Because one would hope that after 1 year of third grade teaching, that reading levels would have gone up by a year, right? One would hope even more, but I'll be happy when my teachers in my district bring everybody up 1 grade level from where they started, right? Okay. This formula, the one I wrote on the board, will always work for that. Okay, which is why this is a better formula than that one in the book. But I'm just pointing out for the examples the book uses, mu1 minus mu2, if the null hypothesis is that they're equal, then this becomes a 0, and it is the same formula that's in the book. Yeah. What's down on the bottom? What's down on the bottom is a little bit of a tricky little thing to write, right? But essentially, it's kind of adding a little bit the variance-ish, the standard deviation divided by square root of n of the first sample and the second sample. It's just a little bit messy, right? N1 corresponds to this first sample. It is how big that sample was. N2 corresponded to this. Sigma 1 corresponded to the sigma for the first population. Sigma 2 corresponded to that population. Okay? Now, by plugging these in and doing the math and then taking the square root, we get the bottom. Up here, the differences, we get the top. Right? Remember, our old one looked like x bar minus mu sigma square root of n. Right? This was for the simple. This kind of looks, this is the difference between the x's minus the difference you would expect, mu1 minus mu2, And then down here, instead of sigma square root, you've got the square root of sigma squared plus the square root of plus sigma 2 squared. And then one, this down here is more complicated version of this down here. Okay? So you noticed when I went to write this on the board, every few seconds you saw me reading the book to make sure I got it right. Why? Because I can't remember this formula all the time right off the bat, which, what do? Not a problem. You go take your stats book, you dust it off, blow the dust off of it, and say, oh, okay, where was that formula for dealing with hypothesis tests between two means? It's 10.2 in the book. So this is my version of 10.2. So if I were writing on your book, I would just, where it says -0, do minus this, right? It makes that formula work for many more cases than you would expect. Right. Okay. I'm going to ask the question, how many of you did I completely confuse? I think this is confusing. So if you don't think it's confusing, then I either did a pretty good job of explaining what we're trying to do, or you guys are much brighter than I was when I learned statistics. Come on, this is a good time to say, hey, we're much brighter than you are. I'm not going to do it. All right. All right. Let us do an example. All right. Oh, before we do the example, this was the first of the formulas, right? It had the sigmas. What if N1 is larger than 30 and N2 is larger than 30? Right? And let's suppose if our samples are big, and instead of getting the population standard deviation, we just can get the sample standard deviations. Okay. What should we do? Well, the easy solution is, as long as n was larger than 30, and now we have two examples, right? This one, we have pulled two samples, one from the first group, one from the second group. If each one of them individually is greater than 30, what does the first one say? Oh, n is greater than 30. Our estimate for S1 is pretty good. So anywhere that sigma is here, you can just replace it with S1 squared and we'll be fine, right? And the same thing would be true over here. And then we just go through life the way it normally would be, and we go develop the z-test statistic, right? Now, one of the little things is I'm not going to get to this state where these are necessarily that different, but what I wanted to point out is if you've got reason to believe that these are the same, okay, if these two are the same and we're estimating what sigma is from the sample of 30 and using it down here, we could have gotten a better estimate of sigma if we had taken what we learned from here and learned from the second sample and somehow pooled them together. If that's the case, there's even a more complicated formula for pooling standard deviations together. It will allow you to make slightly more accurate judgments, right? If you make the assumption that those are the same, that sigma 1 equals sigma 2, right? I'm not going to go into that. Your book goes into it a little bit greater detail, talking about pooled standard deviation functions. All right? All right. We're going to do a problem. Our provost, okay, at the university is running around, and by the way, this isn't true. He's not running around saying this, hypothetically. He's running around saying that our faculty at Texas A&M Kingsville, okay, earn more than 10,000 more than the counterparts, the faculty in Corpus Christi, right? We know our graduating students earn more money than Corpus Christi graduating students. But he's going to make a claim that our faculty earn more as well. Okay? And he says he knows this to be a fact. But he's okay with you testing it just to be sure. Right? But what is it that his hypothesis, the null hypothesis is? Well, that the salaries at TMUC are greater than or equal to the salary at TAMU-CC plus $10,000. Right? He is claiming that our faculty, on average, that the null hypothesis is that our faculty earn $10,000 more than the salaries that Texas A&M Corpus Christi pays their faculty. So this is the null hypothesis. Let us write it down a little bit different. This is mu TMUC. This is mu TAMU-CC plus 10,000. If I subtract these off, mu TMUC minus mu TAMU-CC, subtracting that mu off, those cancel out, is greater than or equal to $10,000. This is my null hypothesis, right? If that is the null hypothesis, what is the alternative? The alternative hypothesis would be what? That mu TMUC minus mu TAMU-CC is less than 10,000, right? That this difference is less than 10,000, right? So we have this. Now, in order to test this hypothesis, what are we going to need to do? Let us go and collect a sample. Let's collect a sample from Texas A&M Kingsville, and we will have to take a sample of faculty members at Texas A&M Corpus Christi, right? So let's assume we do that. For here, let's assume that we are taking 100 students, 100 faculty members, n equals 100. Let us assume that our average salary from TMUC, okay, I'm going to put TMUC Yeah, that doesn't work. Is 89. Right. So we took this sample and let's assume that we knew that the sigma was 4,000. Okay. We take a sample here. X bar is going to be our best estimate of what faculty salaries are in Kingsville. Okay. When we look at this, we're going to have to take a sample of faculty in Corpus Christi. Right? And let's say we come up with that their average is 63,000. That would be what? The X bar TAMU Corpus Christi. Right? And then our sample size, let's say our sample size here was 36. Right? And let's again assume that the sigma was the same. So let's set this one up. All right. So we've got these hypotheses. And I probably should take a picture of it so that, which I can't because I took my phone off. All right. And let me just make a little note. 63,000 and 89,000. N was 136. All right. So we got the null hypothesis stuff, right? So let us now look at what we have. We are looking at X bar 1 minus bar 2. X bar 1 here is Kingsville and CC, right? We believe in the null hypothesis that the differences are going to be greater than 10,000, right? Our null hypothesis had a greater than or equal to sign in it, right? Which means it's a one-tailed test, right? So let's figure out which side in the one-tailed test that we are going to be looking at. Oh, by the way, let us assume that our alpha and sigma are different things. Alpha was going to be 5%. We are willing to be wrong, make a type 1 error 5% of the time. Anyways, we conclude that because the null hypothesis was that our faculty at Texas A&M Kingsville earn more than $10,000, right? Then what we're going to try to do is then figure out when can we reject that null hypothesis. Well, what is it? It's salaries of Kingsville minus salaries of Corpus Christi. What if I get a result that is really, 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 really ridiculous? That salary of Kingsville would be like $800,000 a year, and Corpus Christi salaries would be 23 cents per year. Obviously, extremely ridiculous, right? But what would that mean? It would mean that salary at Kingsville minus Corpus Christi would be a huge number. huge positive number, right? Now, the question is, if we come up with a huge positive number, does that tell the provost he was wrong? What did the provost say? That the Kingsville people make more money than the Corpus Christi ones do. Using this real obvious example, right? The Kingsville people make a hell of a lot more money. They make like $100,000 more, plus that, right? We don't need a stats class. Yeah, if we come back with those answers, we're definitely not going to reject the null hypothesis. So a large number will not mean that we reject, which means a large number is going to be in the acceptance region, which means the rejection region is going to be on the small side, right? So what do we do next? We draw underneath here the standard normal, one that's in the back of the book, and we figure out what the z cutoff value is. We go back into the book to figure out 5% in this tail, what z in the back of the book corresponds to that. Well, as I mentioned, the easiest way to do this is to cheat, to go to the normal, the t-table. Okay, and you know what? I'm going to go to the t-table on your computer. Yeah. Content. Go to the ones, share application screen. Okay, so you guys should be starting to see my screen, right? So we're going to go to the home page, and we're going to go to the t-table. Remember, we were actually supposed to go to the z-table, but I'm going to go to the t-table anyways, because the t-table, when we look at the bottom line here, let me make this bigger. Okay, zoom. Come on. All right. So I zoomed it out too much, but you should see, right? I've got the tail here. I want to know 5% in the region. Okay, so shaded area is 5% in a tail. 5% in a tail is 0.05. That is the middle column here. And now what I'm going to do is I'm going to go all the way down to the bottom. And I end up 1.644. Right? 1.644. So my z cutoff is a minus 1.644. You guys see where I got it? I got it right down here. And this last line would have been the z value. In your book, it's got a minus infinity. All right? So, stop sharing. And you guys should be back at seeing my wonderful face. Is that correct? Share camera. I hear you guys typing something, so I hope that means yes. Okay, good. So we're back to me. All right, so we have concluded that our cutoff value is minus 1.644. We know that our shaded area is the reject, and this area is the accept. All right, region. Now we go find that formula, the test statistic formula. And that test statistic formula was z-test equaled x bar 1 minus x bar 2. This was the differences in our sample minus mu1 minus mu2, what the null hypothesis said those differences should be. Right? All over the square root of sigma 1 squared over n1 plus sigma squared 2 over n2. Now, let's plug in a couple of things. What did the null hypothesis say mu minus mu2 was? $10,000. Right? x1 minus x2. x1 was 89,000 minus 63,000. So subtracting these two off gives me $26,000. So this thing here is $26,000. Down on the bottom, what did we have? Sigma 1 and sigma 2 were both 4,000. And one was 100 observations, and I think this one was 36 observations. Right? So now what do we have to do? We just have to methodically calculate what they all are. Right? So what we have to do is 26,000 minus 10,000 is this top is going to equal 16,000. And on the bottom, we're going to have to take 4,000, square it, divided by 100. Figure out what that is. Take 4,000, square it, divide by 36. Add those two numbers together. We'll get a huge number down on the bottom. We'll take the square root of it, and that will give us our z-test value. All right? Okay. So, how do we go about doing this? You know what? It is 2:44. So what I'm going to let you guys do is from here on out, it would just be doing the math, right? And once we have the z-test number, okay, the last step is to take this z-test number and compare. Is this in the acceptance region? Or is it going to be in the rejection region? In this particular case, we are going to end up in the acceptance region. If you want, you can do your math to figure that out. But you compute all of this, we will get to the point where we accept the null hypothesis that my provost's statement was correct. What does that mean? That means I, as his employee, I am not going to go and tell my boss he's full of shit. that would be a career limiting move on my part, right? I will accept his statement. I will have looked at it to see if there is any evidence he might be wrong. If there's strong evidence he might be wrong. I didn't find any because I found that I was in the acceptance region, and I let him continue to make his statements. Now, let's change this just a little bit. In this scenario, he had the null hypothesis, right? He makes these statements to our faculty or whatever to make us feel good and so on and so forth. And although there might be somebody who's got some minor doubts, he's the boss, right? And yes, he would appreciate somebody telling him if he's wrong, because I believe he's a good provost, and good bosses would like to be told when they are wearing no clothes when they're wrong, right? A good emperor wants to know when he's not wearing anything, right? Bad emperors don't want to be told, right? Work for good people. Now, but we're changing that a little bit, right? And now, our provost is going to make a speech over at Texas A&M Corpus Christi, and he wants to make the same claim, right? Now, he's going to a very hostile audience, right? If he's claiming that he pays his faculty $10,000 more than their faculty gets paid, he's going to say, you know what? I had better have enough evidence to prove my case. Can you redo that analysis? But this time, instead of accepting what I say as the null hypothesis, can you make what I am saying the alternative hypothesis? Right? Because I'd like the people in Corpus Christi are going to continue to believe that they are paid properly, right? Can we change it? And the answer is yes. I just make it the alternative if he tells me, you know, I have the burden of proof. Okay? If you got the burden of proof, it becomes the alternative hypothesis. Anyways, you run the whole analysis over again. And one of the difficulties sometimes is figuring out, is this the alternative hypothesis or the null hypothesis? And the way you got to do that is figure out who has the burden of proof. Okay, with that, I'm going to call it quits. We will continue on Friday, and we will continue to have a test on Monday on any and everything hypothesis testing. Right? Okay, with that, take care. Bye-bye.